Hello guys and warm welcome to QuantPy. We are now going to discuss the Volatilities trilogy. The main objective is to connect the three concepts, that's the stochastic, local and implied volatilities. We will be using local volatility as base. In the previous video we explained the Dupare local volatility model. It assumes the following dynamics for the stock price. So it's similar to the Black Scholes, but the volatility is now a function of time and the stock price. This modification enables the model to match the current volatility surface across the strike and maturity dimensions. So one small change produces a huge impact. As we explained in the previous video, the volatility function can be determined using the prices of call options. The conditional expectation can be written as the function of the conditioning variables, that's the time and the stock price, which is our local volatility function. We explained this relationship in the previous video, but as you would know, this is a standard representation and that we know from statistics that the conditional expectation can be written as a function of the conditioning variables. So we see that the local volatility is the expectation of some random stochastic process, sigma, which explains the connection with the stochastic volatility models. To see the connection between the local volatility and the stochastic volatility using concepts and theorems from stochastic calculus, let's bring in the Gyongy's lemma. Let's say we have a stochastic process, epsilon, which is defined through an Ito's differential, where the coefficients are adopted stochastic processes, and the coefficient of the Brownian is a positive definite, which in the real valued sense means the same thing as requiring that the variance be positive. The W here is multidimensional by the way, but we will specialize it to the one-dimensional case. Essentially, this equation is defined in terms of vectors and matrices, but we will only need the one-dimensional case. So we interpret the variables as real valued, so these are like scalars. And the main presentation change is the variance covariance matrix, which is the matrix delta times its transpose term, becomes the square of a scalar, or shall we say the variance. Now this is quite a complicated process and the pathwise behavior of the epsilon process can depend in a very complicated way on the past values through the random coefficients. No surprises there, as we already know this is quite complicated SDE, so we haven't introduced the Gyongy's lemma to tell us that. Now suppose we are only interested in one aspect of the process, an aspect that depends only on the position and state space, or say one-dimensional distribution. So can we find a simpler SDE that mimics this aspect of the complicated process? The answer is yes, and this is precisely what the Gyongy's lemma is about. It says that there exists a stochastic differential equation with non-random coefficients whose weak solution has the same one-dimensional distribution as the epsilon for every t. It also provides an interpretation of the coefficient of the simpler SDE. Notice they don't depend on the path of the Brownian, they just depend on the current value of the process, kinda Markovian property. The coefficients in the original SDE, on the other hand, depends on the path of the Brownian or the filtration. So this is very much like Markovian projection, but there's some subtle differences. The simpler process, of course, doesn't mimic the full path behavior of the complicated process, but the simpler aspects that it mimics can go a long way. We know same one-dimensional probability distribution means same European option prices, and the interpretation of the coefficients is exactly how we interpreted the local volatility. So we can interpret the complicated epsilon process as describing the dynamics of the stock price under the stochastic volatility model, because the volatility, which is the coefficient of the Brownian, is stochastic, and we can interpret the simpler process as the local volatility model. As the Gyongy's lemma is written in more general terms, whereas our stock price, which is S, follows a specific form, the connection might not be so obvious, so let's try to recast our geometric Brownian in the Gyongy's terms. Let's represent the stochastic version of our SDE of S with the tilde. So this S tilde is now our local volatility model equivalent of the epsilon process. So the volatility in this SDE is an adopted stochastic process. We know to get rid of the multiplicative S, we will need to take the log of S. So let's define a new variable x as equal to log of S over S naught. Now to get the dynamics of x, which is dx, we apply Ito's lemma, which is the first derivative times ds plus half the second derivative times ds squared. Notice S naught is fixed, so its differential is 0. Substituting for ds and ds squared, we get. Combining the dt terms, we get. So the simpler SDE are now in the same form. Now let's do the same for the stochastic version, which is the S tilde process at the top right. So to get rid of the multiplicative S tilde, as before, we define a new process as log of S tilde divided by S tilde naught, which is the value of the process at time 0. Now, if we apply the Ito's lemma, we know we will get an additional term in the drift, which is minus half the variance, so we can just write the result. Now we have the stock price SDE and the same form as the Gyongy's lemma. So we can write the relationship between the drifts using the Gyongy's interpretation of the relationship between the drift of the mimicking simpler process and the complicated epsilon process. Notice our process is defined as log of S over S naught. So that's why the statements after the condition look slightly complicated. Similarly, we can easily read the relationship between the volatility terms. Now we can simplify the conditioning expressions. So these are the expressions after the conditional symbol. S naughts are equal, we can remove S naughts. And then if logs of the two s's are equal, it means the two s's must be equal. So we get. We can apply the same logic to the second equation as well. And now we can see the connection with the Gyongy's lemma. And we can thus interpret the local variance, which is the square of the local volatility in the Dupere model, as an average of the variance of a process whose volatility term is stochastic. So we understand the connection between local volatility and stochastic volatility, and later on we shall show what it means geometrically as well. You can see the local volatility is only capturing the average of the stochastic volatility. Hence, we don't expect this local volatility model to capture all of the properties of the stochastic volatility models, for we know average doesn't capture all the properties of a distribution, so no surprise there. Now let's explore the connection between our local volatility and the implied volatility. We know implied volatility is associated with the Black Scholes model. Essentially, it's the volatility that will make the Black Scholes price match the market price of a European option, call option in this case. So far, our discussion has been in terms of the market prices of call options, independent of any model, and now we're going to introduce the Black Scholes. We know the payoff of a vanilla call option at maturity, and we know that today's price of the vanilla call option is equal to the expected discounted value of the option payoff, where C represents the market price of the call option, and I have suppressed the arguments to avoid clutter. Now we are in the Feynman-Cox territory. We know their theorem establishes the connection between the representation of the price in terms of the conditional expectation and in terms of the partial differential equation. If we assume that the process S is defined by the local volatility SDE, we can write the PDE as follows. So this is the pricing PDE. Solving this PDE subject to the terminal condition, which is the option payoff at maturity will give us the call option price. This is very much a generalization of the Black Scholes, by the way. Remember, we could write the option price as the expected discounted value of the payoff under the risk-neutral measure, or alternatively, we could write the dynamics of the price in terms of the Black Scholes PDE. So the Feynman-Kac theorem pretty much establishes this correspondence between the expected discounted value and the PDE representation of the price. Now, if we represent the Black Scholes implied volatility, that will match the price of an option with strike K and maturity T by sigma underscore BS with the relevant arguments, this K and T. Then we know that plugging this volatility into the Black Scholes formula, along with the other parameters, will produce the market price of the call option that we continue to denote by C. The dynamics of the stock price will then be given by the following SDE. And given that the Black Scholes price is also given by the expected discounted value of the payoff with the same terminal condition, we can use Feynman-Kac to write the PDE for the Black Scholes price. In comparison to the previous PDE, the market price has been replaced by the Black Scholes price, and the local volatility has been replaced by the Black Scholes implied volatility. Let's represent the second derivative of the Black Scholes price with respect to S by gamma, so we get. Now don't forget, we are after establishing connection between the local volatility and the implied volatility, so we will need to find a way to link the two PDEs. To this end, let's construct a portfolio which is equal to the difference between the market price and the Black Scholes price. So we are long one market option and we are short one Black Scholes option in a way. We can differentiate with respect to T. Now we have a way to plug the two PDEs into one equation. So let's substitute the market price PDE and the Black Scholes PDE. Now we can combine the similar terms. The first two are easy. We just combine these sets, factoring the common term. Similarly, we can combine the last terms. By the way, the S's in the two processes, this the local volatility SDE and the Black Scholes SDE, should be different because they describe the paths of two different processes, which are different because the diffusion coefficients in the two SDEs are different. But here we are only interested in the local behavior, so you can imagine the value of both of them at the start of the time step are equal, and we are collecting any differences in the P&L between the two and the gamma term, because the drift terms, this the R times S, are the same, and you can assume that both options have been delta hedged individually. You might have seen something similar in the textbooks when they try to calculate the P&L when the option is priced using one volatility and then delta hedged using another volatility, so you get this gamma term in those situations as well. Were we interested in the paths, then we would have to be careful, just like we saw in the relationship between the stochastic volatility and the local volatility. We named them differently, remember, S tilde and S. Now we know this term is just the value of the portfolio, and the second one is just the derivative of the portfolio with respect to the stock price. So we can write it in terms of our portfolio, which is pi, as follows. The last term requires some extra work though, which is because the volatility terms in the two PDEs are different, so we can't factor out the sigma. To help factor out the sigma, let's add and subtract a term which has the volatility of the market price but the derivative of the Black Scholes. Now we can combine these terms, helping us to factor out the sigma term. And we combine the residual terms. The trick has helped because now this term is just the gamma of our portfolio, so we get. And we can also represent the last term by F. So this is the kind of source term that you see in the ODEs and PDEs. Now we just need to bring back the Feynman calcs. We saw earlier that it establishes connection between the risk-neutral valuation, which is the conditional expectation, and the PDE. Notice when writing the expectation, we suppressed the major Q and the conditional expression to avoid clutter. And the journal version of this theorem, the PDE has a source term, so you can imagine f as some sort of continuous dividend, and the conditional expectation then reflects this stream as well. So the integral aggregates the discounted value of the dividend across time, and the exponential term inside the integral discounts each component of the dividend stream to today. Using this result, we can write the value of our portfolio in terms of the conditional expectation. We have the PDE and we are writing it in terms of the conditional expectation. Now the portfolio is long one option and short an option of the same maturity, the terminal payoffs of which are equal. So the first term is 0. And we can simplify the term inside the exponential. Because r is assumed to be constant, so integral of r over 0 to t is equal to r times t. So we get, now we can substitute the expression for f, which is the source term. So this is now like the expected value of the lifetime P&L of the portfolio. We know the terminal value of the portfolio is 0 because both options have the same payoffs. And the current value of the portfolio is 0 because by definition, the Black Scholes price matches the current market price. So we expect and want this value to be 0. Otherwise, the two will not be the same really. We can get rid of 1 divided by 2 and note that the expected value of the sum is equal to the sum of their expected values. So we get, because sigma bs is constant, we can take it out of the expectation. And isolating sigma bs on one side, we see that the Black Scholes implied variance is like the weighted average of the local variance over the life of the option, which is more visible if we abbreviate the weight terms. By the way, frequently we will be making statements in terms of the implied variance and local variance, so these are just squares of the implied volatility and local volatility. There's another way to look at the relationship between the local and implied volatility, which is more revealing. You know, the original Black Scholes assumes that volatility is constant, but as a trivial extension of the Black Scholes, you can make the volatility time dependent. So if you assume that the volatility is a deterministic function of time, then the Black Scholes formula still holds, though the volatility will be a function of time, so it will be different for different times. So let's write the Black Scholes with the time-dependent volatility, where k and t represent the fact that the volatility function required to match the market price of options with different strikes and maturities will be different because of the non-flat volatility surface. Now, if we repeat the previous derivations with these dynamics, then it's easy to see that f will change as follows, and the value of the portfolio will come out to be as follows. We are just replacing the constant BS volatility by the time-dependent BS volatility. Now, as the Black Scholes volatility varies with time, we have more control and we demand that the expected value of this P&L be 0 for each time slice, where we got rid of 1 divided by 2 as before. We can get rid of the discounting factor and then replace expectation of sum by the sum of expectations to get. As the Black Scholes volatility is deterministic, we can take it out of the expectation, and as before, we can isolate the Black Scholes time-dependent volatility function to get. It's easy to show the link with the constant implied volatility version of the Black Scholes. To see the connection, Apply Ito's lemma to log of S. Now substitute the dynamics of the time-dependent Black Scholes SDE. Same procedure that one uses when solving for S and the geometric Brownian SDE. Now rearrange the terms and integrate. And the constant volatility Black Scholes, we could take the sigma terms out of the integral, but here we can't because sigma depends on time, but that's no biggie. We can easily calculate its mean and variance. Mean is just the deterministic part, and the variance by Ito's isometry is just the integral of the square of the coefficients of the dw term, but with respect to dt. And the original Black Scholes, the volatility is constant, so we can take it out of the integral, and the mean would become. You may remember this in the more familiar form. And we would also have the variance as sigma underscore bs squared times t. So comparing the two variances formulae, we see that the Black Scholes constant implied variance would be the average of the time-dependent implied variance. Remember, integral represents area, and area divided by t represents the average height of the curve. So what we are seeing now is that the Black Scholes implied variance can be seen as the average of the time-dependent variance over the life of the option, where the time-dependent variance at each time t is the weighted average of the local variance. One can represent this in space-time grid. So the time dimension is the integral on the right-hand side, and for each t, the expression on the left-hand side is capturing the space or the stock price dimension. Now for each time, the local volatility is a function of S. It will actually be a surface, but I have only drawn a few curves for illustrations. The same goes for the other terms on the right-hand side, so they will be functions of S. But the left-hand side doesn't depend on S, so it is like a constant for each t. Let's break down the right-hand side of the expression. So this is the right-hand side of the first equation on the left. Let's ignore the denominator as it is kinda scaling. Now in the numerator, we have the local variance, which is the square of local volatility, which we will leave intact. We know what S squared looks like. Now the other two terms, which play the key role here, are the gamma and the probability density. Remember, probability density is hiding in the expectation operator. For the probability density, we know the current value of the stock price. So the time zero probability density is the delta function with mass concentrated at the current value of the stock price, and the density will spread with time because as time moves we will be less certain as to where stock price will go. Now we know from the Black Scholes gamma video that gamma has the opposite behavior. The longer the time to maturity, the more spread the gamma profile, and as the time approaches maturity, the gamma concentrates at the strike price. Now you can combine the density and gamma in one chart, where I change the orientation and perspective so that we can see the shape more clearly. So the probability density starts as concentrated at the current stock price and spreads with time, whereas the gamma is distributed at time zero but then concentrates at the strike price when the option is close to maturity. Now if we multiply the two, we see that their product is like a narrow band hill, starting from the current stock price and ending at the strike price. Now multiplying by S squared is not going to change the shape much because we are talking exponential declines here and S squared is nothing in the scheme of things. Now remember, this is used as weight to average the local variance. This shape suggests many approximations. We see the hill is very narrow. The peak runs from the current stock price to the strike price. So if you don't have time, then you can approximate the implied volatility by drawing a straight line between the current stock price at time zero and the strike price at time equal to maturity of the option, and then averaging the local volatility along this line. Remember, local volatility is a two-dimensional function. So in this simplified approach, you're sampling the surface along a line, connecting the current stock price and the strike price. For shorter maturities, apparently, as we shall demonstrate in a future video, harmonic average works better. If you interpret the volatility as speed, which in a way it is because it determines the speed of the diffusion, then you know the harmonic mean arises naturally in such context. If you take the total distance, divide it into equal segments, and run each segment at a different speed, then your overall speed will be the harmonic mean of the speeds in the individual segments. We know implied volatility kinda represents the overall average of local volatilities, so you can see how the harmonic mean comes about. If you have a bit more time to think, then you can employ analytical approximations to the peak of the hill, which connects the stock price and the strike price, and then average the local variance along the so-called most likely path. So you're averaging along the curve instead of the straight line. You can also imply some kind of geometric Brownian bridge as an approximation. By the way, for the dividend-paying stocks, you won't get such a smooth connection, as you expect payment of dividends leads to jumps in the stock price, so you will have those discontinuities at the dividend dates, but between dividend dates, it should look smooth. Now let's try a slightly different interpretation, which is more probabilistic. The term in the denominator is an average, so we can take it inside the expectation. Now we can interpret the ratio as a density or the derivative of one probability measure with respect to another, or the Radon-Nikodym derivative. Remember the discussion in the change of probability measure videos? We had to show that it's indeed density, which means that we have to show that it's positive and that its expected value is equal to 1. This is because total probability is equal to 1, so the density must integrate to 1 with respect to the relevant measure. And because it's a process, we need to show that it's martingale, and if we do that, then it's a valid Radon-Nikodym derivative for change of probability measure, and we can proceed to simplify the expression by changing the probability measure. It's easy to see that it's positive. We know Black Scholes gamma is positive and the square of S is positive, so no issue there. It's also easy to see that its expected value is equal to 1, because if we apply expectation, then the numerator and the denominator will be equal, so we will get 1. And you may also know that the dollar gamma, which is the gamma times S squared, satisfies the Black Scholes PDE. So just like the option price, the dollar gamma, scaled by the value of the bank account, will be a martingale under the risk-neutral measure. So it is indeed a valid Radon-Nikodym derivative process for our purposes here. But before we proceed to simplify this expression using the change of probability measure, the martingale property might not be so obvious, so let's quickly show that it is indeed a martingale by demonstrating that the dollar gamma satisfies the Black Scholes PDE, which we reproduce here. To show this equation is satisfied by dollar gamma, we will need to take derivatives with respect to S, but this is going to be a long process because two of the coefficients depends on S as well, so that's gonna complicate the derivation. But we can get rid of these variables by switching to the log of S. Remember, this is exactly what we did in the Black Scholes PDE transformation video to get rid of the variable coefficients, and we ended up with the constant coefficients. So we define a new variable x as equal to log of S, and we represent the option price as a function of this new variable with the tilde. Now we need to transform the first and second derivatives with respect to S in terms of the derivatives with respect to the new variable x. For the first derivative, we just use the chain rule, and it's easy to check that the derivative of log of S is equal to 1 divided by S. Now we differentiate once more to get the second derivative. So we apply the product rule to this term, where we had to use the chain rule in the first term as well. Now we can substitute these derivatives into the Black Scholes PDE. So the s and the s squared terms cancel as expected, and we get. Now we can easily differentiate with respect to x as many times as we like. So if v satisfies this PDE, then the first derivative of v with respect to x will also satisfy this PDE, because differentiating this PDE with respect to x will amount to just replacing v by the derivative of v with respect to x, right? So if v satisfies this PDE, then so does the derivative of v with respect to x. We can write this derivative in terms of the original variable s by just substituting from the transformation equation underneath. So $delta, which is delta times s, satisfies the PDE. Similarly, higher order derivatives with respect to x will also satisfy this PDE, but we are only interested in the second derivative here. And if we rearrange the equation at the bottom right, we see $gamma is a linear combination of the first two derivatives of v with respect to x, each of which satisfies the Black Scholes PDE. So $gamma satisfies the Black Scholes PDE, and we conclude that its value expressed in the units of the bank account will be a martingale under the risk-neutral measure. So we can interpret this ratio as a Radon-Nikodym derivative, and we can write the expectation as expected value with respect to the measure P. To see it informally, we can write the expected value as integral with respect to the probability measure. Now we can substitute for the ratio, which is the Radon-Nikodym derivative. We cancel dq's, and hence we can write this as expected value under the measure P. So now we can see that we can interpret the Black Scholes implied variance as time average of the spatial average. This makes sense because we know local volatility is a two-dimensional function, so averaging across the two dimensions produces a single number, which is the Black Scholes implied volatility, or implied variance to be precise. And we saw before that we can also interpret the local variance as an average of the stochastic variance, which kind of means we can interpret the local volatility as an average of the stochastic volatility. To bring it together, let's visualize a two-dimensional grid. So the stochastic volatility at each grid point is a random variable. Local volatility at the same grid point is a conditional average of this random variable. This is conditional on the value of the process in time at that grid point, but it's less obvious that this is also conditional on the filtration as well, by which I mean the information that's available to us today. So as time changes, this would change as well. And the Black Scholes implied volatility is then kinda a weighted average of the two-dimensional local volatility. But for different strikes and maturities, we will be using different slices of the volatility surface, and the weights would be different as well. Remember, the weight is the hill that connects the current stock price to the strike price at maturity. So as the strike and maturity changes, this hill will change. And also as the maturity changes, then the slice of the volatility surface that we are averaging will be changing as well. So that's why for different strikes and maturities, you will get different Black Scholes implied volatilities. So you can see we are simplifying from stochastic volatility to local volatility, and then from local volatility to Black Scholes implied volatility, but we are losing the richness of the dynamics along the way. So if you have more complicated exotic products, the modeling of which requires richer dynamics of the underlying process, then you will need to go up the chain. I hope you enjoyed the video, and I look forward to seeing you in the next.